now I'll give some details about our work in CENTRIC about AI-enabled non-codebook symbol modulations. So a quick brief agenda of the talk today. So in the first part, I'll be focusing on some motivations and performance results on autoencoder-based end-to-end symbol modulation learning. Then I will move to focusing on some practical aspects of the symbol modulation learning, including like some signaling for training and also some link adaptation aspects like dynamic MCS and dynamic CQI computation for learn symbol modulations. Yeah, moving to the first topic of this talk today, autoencoder-based symbol modulation learning. So overall, I mean, the AI is considered to replace some or entire blocks of the file communication chain. So there is the concept of like block by block replacement, where AI may aid or replace some of the blocks in the file chain. There is also the concept of like multi-block learning, where some of the blocks can be jointly trained to achieve like AI native network, and also there could be also an end-to-end learning paradigm where all like 5-layer blocks could be learned jointly to replace or aid all the file chain. So for symbol modulation, when it comes to symbol modulation learning, we focus first of all on like a block by block method, and this is mainly focused on the motivations like the current QAM based symbol modulations are primarily designed for AWGN, and also they are not very adaptable, or they are not designed for some impairments like nonlinearities that exist in high frequencies. And another thing to consider for the symbol modulation learning is its practicality. So for the symbol modulation learning, if it's going to be part of like a file chain block in future wireless communications, you need to define enablers, architecture, and signaling for this end-to-end design. So yeah, the autoencoder based symbol modulation, as I said, is we consider the study a block by block method, where the when in the file chain, the symbol modulation and the modulator are replaced with trainable blocks. And so the learned constellations at the end of this training could be based on the wireless channel properties. So it could be adaptable to UE conditions, so it could be UE specific. However, in like a typical symbol modulation learning scheme, so different autoencoders may need to be trained for each MR modulation or for each input dimension size. So yeah, for to tackle this issue, so we focused on a scalable architecture for symbol modulation, where typically where in a typical autoencoder and a symbol modulation scheme, you would be training for a given MR modulation or a given number of bits, which would cause issues on scalability and adaptability to different number of bits. We focused on like a scalable architecture to support like a large number of MR modulations or large number of input bits by simply like zero padding for unused inputs, which could be discarded at the output. And for a given MR modulation, typically like for training, M bits could be input to the encoder, and then at the output, typically another M bits or LLRs can be output at the demodulator, and this scheme can be applied and trained to cover up to like M star number of number of input bits or 2 memory modulations. So this would enable to use one architecture to use for the end-to-end modulator. So we tested this architecture in simulations. So here the learned constellations and received symbols are demonstrated for initially for AWGN, and the supported maximum number of input bits is 6. So here this autoencoder is demonstrated for different input bits, like even 3 bits and 6 bits. So for the AWGN channel, the learned constellations and the performance is expected, and it follows the regular QAM, 8 QAM and 16 QAM modulations as expected for AWGN. When we change the noise model to include nonlinear phase noise on top of AWGN, so now the symbol modulation learning shows its impact and shows its performance improvement compared to typical QAM modulation and demodulation. So the learned constellations become to be like non-uniform or non-QAM based. So it starts showing some skewed till the edges. And when we check like the symbol array performance, the learned modulations start to show like significant performance improvement compared to regular compared to typical QAM modulations. Yeah, I mean, so this even this simple example shows the benefits of utilizing learned constellations, especially in the presence of like non-linearities that may exist in high frequency communications, like in 5G and 6G high frequency communications. Okay, maybe now I want to move a bit more on to like signaling aspects related to symbol modulation learning. Yeah, first of all, the if the symbol modulation learning would be implemented in a wireless communication system like 5G or 6G, it should involve some training. And offline training, there can be like different methods like offline training, online training. But if we focus on online training, indeed it would require like significant message transfer between base station and the UE side. So because I mean for the training, there could be like feed forward and back propagation messages in between, for example, the network and the UE to train this model. And so at each like training, there must be some training symbols that are sent from the network to the UE. And again, at each training iteration, several like error values need to be back propagated from the UE to the network, and in which case like these error values could be represented with the floating numbers. It would create a huge feedback overhead, which would be scaled in terms of like the number of training, the size of the network, the training data size. So it could incur a large overhead. So yeah, to overcome like the shortcomings of such an online training, offline training is an option, of course. So offline training models can be deployed at network and the UE, but in that case, so this may not reflect the channel conditions or some specific conditions of the UE. However, these offline trained networks can be used as like an initialization for online training or like a fine-tuning training, so which may reduce the dimension of the messaging in between network and the UE. And so in this case, what needs to be done is like some some codebooks of neural networks could be defined, and then the structure of the offline trained models can be existing in both sides, like both the network and the UE. And then prior initializing this autoencoder based symbol modulation and demodulation, so the network can send like an initial neural network configuration to the UE, and then the UE and network may start fine-tuning if required. And to do that, also there needs to be some procedures to achieve this, and new procedures has to be defined, such as defining some training reference signals. So training reference signals is required if, like, even in fine-tuning scenarios, because the output of the symbol modulator is not QIM based, so it needs to be sent within some new reference signals, which would carry this non-QIM based new complex symbols, which can take any value. So for that, some on the OFDM resource domain, some TRRS reference signal can be defined, and it could be reserved only for the fine-tuning or online training of the symbol modulator. And in addition to this, like, new procedures could be defined, such as the network and UE agreeing on an initial neural network, and some procedures on initial testing of the model, whether it is working as expected, again, based on this concept of training reference signals. And that if needed, some retraining decisions should be given, and then fine-tuning with potential lower overhead could be started. So which means some a short period of online training, and then also some monitoring of this trained autoencoder has to be done to show that this scheme actually could work. Yeah, another aspect on top of the training or symbol modulation learning approach, another aspect is related to the mechanisms related to link adaptation, such as like dynamic MCS and dynamic CQI. So the learned constellation shapes, as we showed, like, bring this performance improvement in terms of bit rate, symbol rate, and throughput. But if these like new learned constellations are integrated to 5G or 6G, it would bring new challenges for link adaptation. This because like the legacy MCS tables are fixed and based on this QAM based modulations. And another aspect of link adaptation is the channel quality indicator, which is like a fundamental feedback to select the modulation order at the network side. And in addition, the channel state information reference signals, the CSI-RS, are based on also the typical QAM, legacy QAM symbols. So if this symbol modulation learning and learn constellation shapes are integrated into these systems, this leads to the need for updating the link adaptation mechanisms, such as updating MCS and CQIs. So in this sense, so the dynamic MCS mechanisms needs to be defined. So the legacy MCS table, for example, is given here, which is designed for a fixed legacy QAM-based symbol modulation and demodulation. However, in learning-based system modulation approach, since new constellations can be defined, and they can be defined dynamically and dynamically agreed between UE and the networks, so new messaging and signaling mechanisms are required so that the UE and network agree on some constellation shapes. So, I mean, just simply these like mapping tables, bit to symbol mapping tables, must be agreed in between the UE and the network initially, and then an association between these new constellations and the MCS table must be established. So another step forward is updating the CQI mapping, which is like a fundamental block for determining the MCS. So basically, UE measures the channel, it feeds back a CQI, and the network decides on which modulation and coding rate to use. However, in the typical CQI computation mechanisms, it is usually implementation specific. So the UE has to map the SINR to CQI based on its capabilities, channel estimation quality, receiver algorithms, etc. And so it is usually done offline, and each UE may have a slightly different SINR to CQI mapping, and it may be even proprietary and implementation specific. So for again, to enable such adaptive symbol modulations, then some dynamic mechanisms to map the SINR to CQI may need to be defined, and a relatively efficient solution is to define some relative tables, like appending some relative indices or relative metrics to the existing CQI tables, so that the UE can its own or proprietary or implementation specific mapping mechanisms to compute the CQI feedback for a given specific constellation shape. And here there can be two examples. So one could be some SNR offsets with respect to legacy tables, or even some relative indices from legacy tables can be assigned, and the network can provide this information to the UE, and the UE can update its own SNR to CQI mapping. So another practical aspect could be related to the reference signals, like CSI RS signals that are used to measure the performance. So in legacy systems, as we know, QPSK-based symbols are used for reference signals to measure the channel. But if constellation learning is enabled at the UE, now the UE may receive reference signals with a learned modulation, so they will be non-QAM based. So in this case, the UE may be able to decide on which type of reference signal to use. It may be scheduled with both legacy and non-QAM based reference signals, and then like compare the channel measurement performance metrics. And based on these comparisons, so do you then the type of the reference signals can be defined. So, and this is like one another aspect that that needs to be handled if symbol modulation learning is enabled in future wireless systems. Yep, I guess those are all that I want to share. So in summary, so the end-to-end learning for symbol modulation shows promising results compared to legacy techniques in terms of like throughput and bit error rate and symbol error rate. And we have like defined some scalable solutions for symbol modulation learning to support so N-area M-area modulation. So it increases the efficiency of integrating these learning-based mechanisms. And we have also shown that like online training may bring significant overhead, and a solution for this significant overhead could be a hybrid mechanism, like starting with an offline trained models and applying them fine-tuning and some defining enhanced signaling to achieve this. So another practical aspect we discussed is about the link adaptation. So link adaptation will also need to be enhanced through some mechanisms, through dynamic MCS, CQI, and defining the new reference sequence.